spent. So I'm looking forward to spending the next few days here and interacting with the members of the Institute as well at the NARA Symposium. The talk, the systems relevant to this talk will be primarily coming from the solid state physics. However, the language, the tools, the ideas will go back and forth between solid state, soft condensed matter, mostly on the classical side of things, but I'll also make some comments concerning some potential quantum aspects. Topic is quite broad. Obviously, I'm not going to discuss these topics in full generality. I will quickly start focusing on something rather concrete, specific, but nevertheless, at the same time, I will try to build up an angle that we feel might be of rather general relevance, of rather general interest. So that's my aim is kind of twofold. Convey some general ideas. I'm not going to be too technical. I'm going to try to focus on ideas, lots of pictures, lots of hand waving. But as an illustration of these general ideas, I will focus on a certain conceptual example, as you will see. The work has been building up over a few years, owing to my former postdocs, students, who are now scattered over several continents. Let me primarily acknowledge my current group members, PhD student Qiu Dao and postdoc Eric Klein-Herbers, who are current members who are continuing to work on these topics. And the one specific focused project that I will discuss is really due to the work of these two guys. All right, even though this is a solid state talk, by way of introduction, let me come a little from afar. Actually, like introducing the aspects that have to do with the interplay of geometry, topology, and energy, actually drawing some inspiration from biology. So the next two slides are going to be just for fun. They're rather tangential to this talk. But nevertheless, this will be a way for me to sneak in the kind of geometrical objects and the kind of energetic considerations that will be relevant also for us. So a few words about motility. It depends. Well, motility has to do with motion, natural mobility of animals, particularly in some fluid environment. It has to do very much in the fluid environment with the size of the animals. On the larger end of some size distribution, we have a fish, a whale, large animals associated with a very large Reynolds number. Large Reynolds number, which is proportional to the size of the object moving through a hydrodynamic environment or hydrodynamic environment moving relative to the object. Large Reynolds number means inertia dominated dynamics. Small Reynolds number relevant for bacteria mean viscosity dominated dynamics, and that affects the evolutionary strategies that evolved to appropriately benefit from the aspects of the Navier-Stokes equations and utilize those aspects for efficient motility. So on the smaller end of the size distribution, we have bacteria. Motility stands for bacterial ability to swim using metabolic energy. Typically, it's some elongated object of this sort with a bunch of flagella at the end, which are helical appendages with a little motor attached that attach these appendages at one end of the bacteria. All of the appendages have the same helicity. All of the motors are rotating with the same chirality for bacteria to move, let's say, forward. Typically, the motors can also reverse the motion of the chirality of their motion, and then the bacteria can move backwards. Small Reynolds number, so it's viscosity-dominated hydrodynamics, as I've stated. Thus, the motion is based on a continuous transduction of chemical into mechanical energy. For larger animals, like clams, fish, clams, the story changes. The motion is inertia dominated. So typically the strategies of motility rely on discrete events, nonlinear discrete events with inertial coasting in between. Turns out, I was amused to find out that the person that contributed to the studies, one of the persons contributed to the studies is Edward Purcell, of course, very famous in the solid state physics and NMR pioneer and solid state physics Nobel laureate. So that's one of the quotations attributed to him that has to do with these kinds of pictures. Vortex shedding has to do with fast fluid motion relative to objects which are not streamlined. So this is not your typical Shinkansen train. This is more like object with something more like a sphere, a circle that's not very well streamlined, fast enough hydrodynamic flow relative to such non-streamlined objects at some critical velocity start producing a sequence of vortices, and the vortices emanating sort of in the wake, emanating from this particle and in the wake of its motion. It turns out It turns out that the strategies to often you don't want vortex shedding. The animals might utilize vortex shedding for their motion, but this kind of passive vortex shedding is actually highly detrimental to structural integrity in civil engineering, also very much relevant for design, like aerospace designs. So if you want to, one issue my civic engineers worry about, as it turns out, as I've learned, is matching of the frequency of the vortex shedding with some natural frequencies of the structure, like a bridge or a smokestack. So to minimize, it's often desirable to minimize vortex shedding. And amusingly, in order to do that, you have to streamline the object. One way to streamline, of course, is completely change its shape, but another way to streamline is to embellish your object with some, again, some kind of spiraling structure. So this little spiral here is designed to streamline the airflow and minimize vortex shedding, so that to prevent the possibility for the stack to start resonating with the physics of the vortex shedding. Anyways, this is just some fun facts. You can look it up on Wikipedia, but you'll see these facts also manifesting in our story from a completely different perspective. It was very different goals inside. Okay, so having said that, let me flash the kind of systems that are of direct interest for the talk. So one conceptual device that I will be dancing around as I am building up my story is depicted here. So that's going to be sort of a prototypical conceptual device. I will describe the physics that plays out. I will propose some, again, somewhat conceptual, maybe at some point practical potential utility of such devices, focusing on such devices for energy storage applications. I will emphasize the interplay between geometry, topology, and the interconversions of energy. Kind of like metabolic energy is converted into some useful mechanical energy in the case of bacteria. Here we'll be converting electromechanical energy into free energy of certain topological textures. I'll discuss how that plays out and try to formulate the language for discussing efficiency of such devices. And again, even though I'll focus on some specific examples, some of the things we've learned will be, we feel, of very much general relevance in the context of, and in broader context than just this specific device. All right. So, what is this device? Well, it's a magnetic insulator again, let me make some specific assumptions, but we might deviate from the specific assumptions as you know, we can discuss. You can ask me like, well, it does have to be an insulator, could be a metal. Yeah, we can look more broadly into possibilities, but just to keep the language simple and you know, focusing on the most minimalist aspects, let me retain just the minimal features that I will need for my story. So suppose this blue film is a magnetic insulator coating some featureless insulating core. This pink wire is a metallic wire wrapping in a helical fashion. It's going to be important that it's wrapping in a helical fashion around this magnetic insulator. So electrical current is sent through this wire, and this electrical current is going to do something to the magnetic dynamics in the film. Specifically, I want to get into a regime and appropriately adapt the symmetries of this device such that this electrical current is able to induce vorticity motion along the axis of the cylinder. So that's going to be a key physical process that I'm after. In the end, I'm after the interplay, more broadly speaking, I'm after the interplay between electrical currents in some more general electrical circuits on the one hand, and topological charge currents, such as fluxes of vorticity. This could be generalized to other topological flavors that we can discuss separately, but just as an example, I'll focus on fluxes of vorticity, again, in the sense of a transport hydrodynamic phenomenon, such that the energy can be interconverted between electrical circuits, and the description that in the end I will try to also depict in a kind of circuit, some effective circuit constructions for the topological charge flows. So we're going to have electrical circuits, we're going to have topological flux, topological charge circuits, and through some physics cropping up at the interfaces here between some magnetic insulator and this electrical wires, I'm going to have energy interconversion between one and the other, and we'll try to understand the efficiency of that energy interconversion and the kind of utilities that may arise from it. The physics is going to be interesting in its own right, but it's even going to be even more interesting, I think, to think of practical utilities of such systems. So the punchline that I'm going to get to in the end is the ability of such helical electrical wires to produce certain what's in spintronics is called spin transfer torques at the interfaces, which will push vorticity flux along the axis of the cylinder. That vorticity flux will lead to the buildup of magnetic winding azimutally around the cylinder. That magnetic winding buildup will store some free energy, so that will be kind of the energy input from the electrical to the topological circuit, and I can play this physics sort of in reverse, in the Gonzaga reciprocal sense, to translate, to transfer this vorticity back into the electrical circuit as a kind of topological motive force. Okay, so the topics, the aspects I'm after here are listed here, and I want to enable novel topological transport phenomena based on magnetic order parameter controlled via geometry. So again, illustrative will play an important role. Utilize the topology of collective magnetic textures to transduce energy between electrochemical energy and the free energy of stable magnetic configurations. I will focus on sort of electrical input outputs, but equally well, you could replace electrical input outputs also with thermal. So more broadly, thermoelectric input outputs. And I like to quote Pierre Curie in this context, saying symmetry creates the phenomenon. Of course, as we know, symmetry constrains phenomena. Reducing symmetries allows for more things to happen. So I will use geometry and the reduction of the symmetry as dictated by geometry. For example, this geometry breaks inversion symmetry, so the structure is chiral, as a way to kind of open up certain new phenomenologies that would not be present in sort of simply geometrical structures. Okay, So let me take a minute to fall back on some idea we proposed a few years ago on how to use topologically stable magnetic textures and how to control those topologically stable magnetic textures in practical electrical devices for energy storage. Okay, so it's a basic energy storage idea that will underlie much of what I'm going to say later on, at least as an overarching concept. Later on, I'm going to improve ways to control this energy storage, but the idea from that old paper, the essential idea, is already illustrated in this cartoon here. So the idea was the following: if you imagine for a second a mechanical rod. Imagine you're able to take the rod, twist it at the end, glue the ends, let it be, store free energy in the mechanical distortion that way, and go backwards. Cut those ends open, sort of unbend it, untwist it, and convert that twisted motion through some dynamo into electrical circuit. And imagine you're able to do that, in an efficient way, integrating this twisting and twisting motion with some kind of electrical circuitry. Of course, it's possible, it's consistent with thermodynamics in principle, but how do you make a real device based on that? Of course, very difficult to imagine, but it becomes much easier if you replace mechanical twisting distortion with something similar, but in the spin space, in the magnetic order parameter space. Okay, so in the end, you could imagine a device which is geometrically, structurally fixed. Let's take a loop. Made out of magnetic material, which locally has, well, the order parameter locally has a strong easy plane anisotropy. So the order parameter, let's for simplicity suppose it's a vectorial ferromagnetic order parameter, even though that could be generalized to other types of order parameter, as long as the topology is the same. Take that vectorial magnetic order parameter and allow it to twist in the local easy plane, and the same happens at every point of this loop, such that in principle we're able to twist up the magnetic configuration into spiraling states. Now, in the equilibrium, suppose it's a ferromagnet. Okay, the ground state has uniform magnetization. The twist would have some free energy cost associated with it. Spintronics has tools to allow that to happen in principle. Through spin Hall effect associated with electrons. So let's wrap some electrical current at, as shown here. You could design spin transfer torque physics. Essentially, it's based on exchange interactions between electrons at the interface and magnetic texture. You could design a spin transfer torque physics which produces torques, essentially realizing this in the magnetic system. So sending electrical current through the structure, the torques are producing boundary conditions with a tendency of the magnet this end at this end to twist up. That could inject free energy into this loop, and you could, if you can do that, the reciprocal must also be, the inverse of that must also be possible. So if you, by sending electrical current, if you can inject free energy into the system, the reverse process of that magnetic configuration unwinding, naturally relaxing towards its ground state, should produce electromotive force that will eject energy into the electrical circuit. That's what's kind of the basic idea. I don't know, if anybody here is expert on spin transfer torque physics. So I'm not explaining the microscopic nuances, but I guess it should be, why not? It should be at least acceptable. It's not surprising that the moment you turn on exchange interactions between electrons and the ferromagnet, if the symmetries allow electrical current to wind up magnetic texture, in principle, that might happen. And in practice, again, using spin Hall effect, inverse spin Hall effect, we can enable this twisting and twisting motion that allows us to interface electrical currents with magnetic dynamics. That's the basic idea. So one more ingredient here is the ability to effectively perform this kind of cutting, gluing, cutting and regluing action, because we want to be able to disconnect magnetic order here and here to be able to twist the two ends, and in a magnetic system that could be easily accomplished by, for example, locally heating up a section of this wire above the ordering temperature that destroys stiffness of the magnetic order parameter here, allows us this ends to kind of flop around freely, and then lowering temperature, we would go back and sort of reglue the magnetic configuration. That's kind of the basic. That's the basic idea. I hope it's clear. If anything isn't clear, please ask me now, because it's sort of this essential idea is going to be underlying much of what I'm going to say later. The practical questions are still at the end of this paper. We're kind of remaining, namely how to do it. This injection extraction of winding in practice efficiently. In principle, we can do it. How to do it efficiently in practice was still rather an open question. Related question: what would be again most efficient in practice way to control symmetries of the system to allow this physics? We can control symmetries. We can follow two strategies: either by kind of controlling heterostructure through interfaces. We could break inversion symmetry, for example, or using a geometry, going to twisted, curved, sort of twisted, so to say, structures, and then using geometry to control symmetry. So we can choose between those two. I will touch upon both of this, but the focus is going to be more, at least for the purpose of this talk, building up towards geometrical controls. That's what's in the title of this talk. And finally, the question that only rather recently I think we put on really solid grounds is how to think of the thermodynamic efficiency of such devices, how to generally, in some universal sense, think of the efficiency of the crosstalk between topological dynamics and electrical, also of electromagnetic dynamics in the system. So I'm going to address that question systematically. Okay. So thinking about especially the first two questions that I've raised soon after the original proposal, we shifted to a slightly different approach. Rather than starting with one-dimensional system and twisting the ends, let's extend the one-dimensional, quasi-one-dimensional system into 2D. And rather than twisting the ends, and this L is showing again some kind of curve where we're gonna, it's like maybe like a physical magnetic system, magnetic wire that we want to wind up to put free energy in the exchange interaction associated with this winding configuration. Rather than injecting that winding at the ends, as I've just described, let's inject that winding in a two-dimensional sense by pushing vortices across, magnetic vortices in the two-dimensional, kind of extended two-dimensional space, pushing magnetic vortices across this magnetic wire. Okay, so now it's not the ends which are utilized for the input-output, it's the entire length of the wire that will be utilized for input-output. So clearly, conceptually, it seems like an improvement, as long as we can we can realize effective controls over the motion of vortices. Okay, and it turns out that is quite possible, and we believe this is probably the most appealing way to control winding. Once you go to 2D, now it's not only the sort of geometry of one-dimensional system like a loop or some kind of curve, but now it's the geometry and curvature of a two-dimensional membrane within which everything is living. That's going to be that may provide the control of the geometry, may provide some additional knobs for controlling this physics. In essence, if you, especially for those of you who are familiar with superfluidity, superconductivity in low dimensional systems, it's useful to connect to that at this point. If you have one-dimensional superconductor, superfluid, it's very easy to inject winding. You simply send a superflow along this one-dimensional channel that naturally produces wound-up textures. Those wound-up textures, in fact, in this case, they relax through the vortices moving transverse to a one-dimensional superflow. So such interplay between a vortex motion and winding is detrimental to low-dimensional superconductivity. Either one-dimensional superconducting channel or two-dimensional superflow wound up by sending an electrical current, in fact, naturally unwind by shedding vortices in the transverse direction. That's called phase slips, and such phase slips generically dominate dissipation in one-dimensional, two-dimensional superfluid superconductors. So what we need to learn to do on the other hand in the magnetic system is to kind of reverse this phase slip unwinding process. That's going to be our goal. We want to be able to grab directly onto the vortices, unlike in superfluids in which these vortices are kind of passive objects that naturally appear as a kind of relaxation channel. We want to devise tools to grab those vortices, push them uphill kind of in the wrong direction, energetically in the wrong direction, and utilize that control to rebuild superflow and to restore the free energy associated with the superflow. That's kind of what we're after. Okay, a little technical slide just to put some, just to introduce some basic mathematics that we will be building our physical story of concerning this picture that I've shown on the previous slide. Imagine a two-dimensional magnetic film. For simplicity, suppose we have three-dimensional vectorial order parameter. I'm depicting here the projection of that three-dimensional order parameter, like a magnetization or a nail order parameter in antiferromagnet, projection of that order parameter onto the plane. I will focus on sort of, for starters, kind of natural spontaneous proliferation of vortices and antivortices. It could be something that you've encountered in the context of BKT physics. Similar things happen in pneumatic liquid crystals, superfluids, various XY models. So generically, in those contexts, you have at finite temperature, vortices, antivortices, binding, unbinding, so spontaneous proliferation of vortices, antivortices would play a role, and that's also the case in my story. On the one hand, on the other hand, if you look at a patch of such a two-dimensional magnetic film, there is an interrelationship between winding on the boundary of the patch and vorticity in the interior. Here I'm stating some basic aspects of this interrelationship that I'm going to refer to as vorticity winding and transmutation that will allow me to essentially, for example, grab onto the aspects of the vortices, move them around, and convert the motion of the vortices into winding. I'm going to be storing my free energy into winding. I'm going to be building, not just storing free energy, but generally building some kind of circuit ideas about topological, what will become later, topological hydrodynamics, with a primary focus on the winding. So in that sense, vortices just act as sort of auxiliary mobile objects that I'm going to use to control winding and unwinding. Okay. So that interrelationship between vorticity and winding is captured in the simple relationships. For example, integrating over the boundary of this patch, let me define net winding in this fashion. Phi is the polar angle within the plane of the order parameter. M parallel is the planar projection of my vectorial order parameter. So that's the definition of winding. And according to Stokes' theorem, you could prove that, well, if you think of this this winding, if you can express it as a kind of line integral of a vector field, invoke Stokes' theorem, you can easily show that this contour integral that defines the winding is identical to the area integral of the vorticity density defined in this fashion. In the strongly ordered, strongly easy plane limit, this vorticity density integrated over the patch would be quantized in as an integer number, with vortices having basic vortices having charge +1, anti-vortices having charge -1. But it turns out, even for far away from a strongly ordered, strongly easy plane configuration, the notion of vorticity and vorticity winding sort of interconversion, transmutation are very much relevant and very strictly governed by this kind of bulk boundary correspondence. So even in a strongly fluctuating system, there's a strict correspondence between net winding on the boundary defined in this fashion and the net amount of vorticity for a fluctuating system not quantized, defined in this fashion in terms of the vorticity density. Okay, because of the Stokes theorem, the vorticity, the net vorticity is preserved. So any kind of local fluctuation of the order parameter do not affect the total net vorticity, because the total net vorticity can only be modified by something going through the boundary. So that naturally leads to a continuity equation that relates the transport of such vorticity density to the continuity equation allows us to think of the dynamics of vorticity density as a transport phenomenon governed by the vorticity flux defined in this fashion, where I and J stand for spatial coordinates, so this temporal coordinate. The vorticity flux is first order, involves first order spatial derivative, first order temporal derivative. Vorticity density involves two spatial derivatives in this fashion. So the key relationships here, kind of takeaway messages, there is a strict correspondence between winding on the boundary and net vorticity in the interior. Easy to understand that in the strongly ordered easy plane regime, because vortices then sort of come in a quantized fashion. When vortex passes through the boundary, then the net vorticity changes in multiples of 1, and the next winding would change in the multiples of 1 correspondingly, but it's actually true more generally in a fluctuating regime. And the other fact is the existence of a continuity equation that allows us to construct kind of a hydrodynamic description of the transport of vorticity. Okay. Any questions? Maybe students? Oh, yeah. Yes, no, it's yeah, good question. Let's normalize. M is normalized here, such that in the strongly ordered, let's say, in zero temperature, close to zero temperature, its magnitude is 1, and it's fluctuating close to the XY plane. Okay, but in principle, it could be anything. What's that? What does n parallel stand for? That's the in-plane projection of, let's say, having in mind vectorial order parameter. Okay, if it's some kind of XY order parameter, maybe n parallel is just is the whole thing. Okay, so back, okay, with all of this in mind, under our belt, let's go back to our conceptual device. Think of it as a conceptual prototype based on which we'll develop our hydrodynamic as well as circuit ideas. Okay, so starting from kind of building things up from ground up, some basic condensed matter system, some basic theory, basic dynamics. We want to then cross-grain it into some kind of hydrodynamic description, and then ultimately develop some kind of circuit theory on top of the hydrodynamic description. Okay, so it's like going to higher and higher and higher level in the construction. That's kind of a picture of the sort of circuits that I'm building towards. Okay, so back to our conceptual prototypical device. Again, 2D magnetic film. Later on, I'll tell you how to properly develop analogous description as formulated on the previous slide in the curved geometry. Turns out in the curved geometry, you could also formulate naturally kind of vorticity hydrodynamics. I'll tell you about that. I'll formalize that later, but now, again, just believe me that just as in the case of the flat geometry, curved geometries, we can also formulate such a nice conserved hydrodynamics of vorticity. And now, as I've already advertised, I want to be able to interface electrical current flowing through this helical wire on the one hand with net vorticity flowing along the cylinder. That flow of net vorticity is building up, as I've just described on the previous slide, is building up winding azimutally. So if you take a cut, a cross-sectional cut of the structure associated with the net vorticity flow, you should see magnetic texture winding up or unwinding at any cross-sectional cut. So clearly such winding up would be associated with some free energy cost. Okay, so if you, for example, pass a single vortex from left to right across the entire structure, that will change winding by 2 pi or something about comparable to 2 pi in the case of a finite temperature fluctuating system at any cross-sectional cut of the cylinder. So the passage of a single vortex across the system will change the free energy of the system in proportion to the length of the system. That will be, the change in the free energy will be described by this capacitive element. This blue circuit here describes my, basically it's my circuit description of the basic coarse-grained vortex dynamics in this device. R sub V is the impedance of vortex motion across the cylinder, like the total impedance is proportional to the length of the cylinder. It's sort of like the equivalent of the Ohm's impedance, but for motion of vorticity. In the strongly ordered regime, when vortices are topological point-like defects, you could expect them to behave as some kind of point-like quasi-particles, naturally. In this strongly fluctuating regime, it's no longer true, but the patches of vortices and antivortices, you can still imagine that the patches of vortices and antivortices obeying continuity equation moving around should still obey some relationships analogous to Ohm's law. So we're able to define the total impedance associated with the net motion of vorticity across the system. And again, C sub V is going to be the analog of capacitance that corresponds to the energy stored in the winding configuration as a result of vortices moving across the system. Okay, that capacitance will be inversely proportional to the exchange energy. So that's my effective circuit for the vortex dynamics. That's already there even in the presence of this helical wire. The helical wire on its own is just ordinary electrical circuit. It has, again, some resistance associated with it. It has some inductance. We can couple, even though we may not have direct coupling readily available for vortices. We do, of course, have direct coupling to the electrical charges. So there's some voltage source. That's how we are inputting energy from the outside world into this combined system, and that's where the energy will come out if we want to extract the energy from this combined system. So the full device in the circuit depiction looks like this. The key is the element that I'm characterizing by some calligraphic R that quantifies in the end of the day, will quantify the effective drag between electrical current flowing through this helical wire and the vorticity flowing along the axis of the cylinder. Okay, the effective drag. How does that effective drag? How is that effective drag constructed? Well, it is constructed based on microscopically based on the spin transfer torque physics. Tau spin transfer torque is the transfer of spin angular momentum. So that's a notion that we take from spintronics. in the presence of electrical current flowing through this wire, microscopically, let us look at the transfer of spin angular momentum from the electrical wire into the magnetic system. That's what the spin transfer torque is. And let me calculate the power, the input power mediated by spin transfer torque that transfers energy from the electrical system to the magnetic system. That input power is proportional to the torque times the angular velocity, and I integrated over the length of this wire. Okay, just like the work associated with linear motion been given by the force times the velocity, the work associated with angular motion, that's a torque times angular velocity, and it works in the same fashion both in real space and the order parameter spin space. Okay, so if you now just for a second imagine that the right-hand side of this expression boils down to here R is just some phonological coefficient, so some proportionality coefficient. So this expression boils down to the product between electrical current I and the vorticity current I sub V. Then from the point of view of electrical current, this work appears as a voltage source. In an electrical circuit from a battery, the input power is given by V times I. So from the point of view of electrons I, R times I sub V, that's an effective battery, effective voltage source from the vortex dynamics acting on the electrons, and vice versa. From the point of view of the vortex motion, R times I is an effective voltage source that is acting on the topological circuit. Okay, and there's only one proportionality coefficient that's relevant from both sides. And in fact, it reflects on-Zeiger reciprocity between these two hydrodynamic entities. In essence, we have, in the end of the day, that's what I'm going to depict on the next slide. In the end of the day, think of the vortex motion and electrical motion as two hydrodynamic flows with some drag between them. And the calligraphic R is simply parametrizing the strength of the drag, phonologically speaking. Okay, so in the end of the day, this two hydrodynamic flows, and in simplest description, might be described by such on-Zeiger reciprocal response relationship. So these are the fluxes, these are the conjugate voltages, the impedance, electrical impedance, vortex impedance, and this is on-Zeiger reciprocal drag between them. Because we typically in our geometries, we're interested in sort of this kind of cross flow. You should think of the drag as a kind of Magnus drag. Electrical flow exerts a Magnus force on vortices, and vice versa. Vortex motion exerts a kind of a Magnus back action on electrons. So that was second kind of improved proposal a couple years later from our original proposal, in which so remember the original paper was from 2018. Now there's kind of a second paper in this line of work in which our device evolved. Now we're we're thinking of focusing on the vortex motion, and we have this is my electrical wire, this is my magnetic annulus. We proposed for such a device to be carved out of a two-dimensional film. So you start with a two-dimensional film, drill a hole in the middle. Basically, it has topology of an annulus, define some boundary on the outside, and then in the end of the day, we have the interaction here between electrical current circulating azimutally, and then the vortex motion radially. So we're realizing this kind of cross-coupling between sort of Magnus cross-coupling between electrical current and vortex current. So this is the simplest prototypical device in the flat geometry from the symmetries point of view. To enable this calligraphic R, to enable this Magnus force, you can convince yourself that this metallic contact itself has to be, this metallic wire itself has to be magnetic. So in addition to magnetism within this kind of easy plane magnetic film, the metal itself has to be magnetic. Otherwise, from the symmetry, you could, from the symmetry point of view, you could rule out this Magnus cross-coupling. So that was essential in our proposal a few years ago. Next, I'm going to replace the magnetism of this metallic wire with curvature of the magnetic film wrapped around the cylinder in conjunction with the helicity of the metallic wire. So it turns out that that's kind of one of the key punchlines concerning geometry in the title of my talk that I'm building towards. I'm going to replace this more complicated heterostructure with a much simpler heterostructure in which the magnetic elements that inject torque into my easy plane film are going to be replaced by a certain geometrical character of the device. That is what I'm building towards. Just few rather tangential but actually important points to be made along the way is that so far everything in terms of specific relationships like that Stokes theorem, continuity equation, that those relationships underline our construction are all based on some classical coarse-grained description of the magnetic dynamics. And you may wonder, well, would that survive if we go down to a microscopic scale, for example, fundamentally some spin lattice scale, and in particular if we account for more general thermal and quantum fluctuations, whether the aspects that we crop out of that effective coarse-grained description, whether they will survive, and the answer is yes. So the fundamental theory, in fact, looks a bit different from the way a more fundamental theory looks a bit different from the way I've told you so far, but at the most fundamental level, turns out there is nevertheless a continuity equation. Okay, that continuity equation is constructed for vorticity, the most basic microscopic vorticity defined per plaquette of a larger two-dimensional lattice. Even more fundamentally, I should have defined the plaquette triangular plaquette. Doesn't really matter. So if you can break down any lattice could be triangulated into some triangular plaquettes, but here I'm showing it for a square plaquette. The essence doesn't change. The continuity equation at the most fundamental quantum level looks like this. These are now quantum spins fluctuating at the vertices of a lattice. The vorticity per plaquette is defined like this, is defined in terms of the z component of the quantum vector chirality that's given by the sum over the edges of this plaquette of the vector product of quantum spins adjacent to each other along one of these four edges. So there are four contributions, 1, 2, 3, 4, this cross product between the adjacent spins. That's the definition of vorticity, quantum vorticity per plaquette. And I'm not writing out the definitions of these fluxes, but you could define, again, quantum mechanically in terms of, microscopically in terms of Heisenberg equation of motion. For any general Hamiltonian, this J's I defined as some expression that involves commutators of the spins with whatever your Hamiltonian is. Again, it's a topological relationship. It's insensitive to the details of the Hamiltonian. With the fluxes defined per each of the four edges of the plaquette. It's valid for any Hamiltonian. For smooth classical textures, this is kind of backward compatible. Okay, so it fundamentally works, and then in the kind of smooth semi-classical regime, it reproduces the previous construction. So it's fully backward compatible. Okay. I'm gonna skip this. We can think of this physics playing out in natural materials. You could also think of this physics playing out in artificial materials, like the kind of systems which are nowadays developed in the context of quantum computing, quantum annealing. So this is an example of that. This is an experimental system. It's actually despite looking so pretty, it's actually an experimental. It shows some experimental data. That's just to make it some connections to already prior existing experiments. So this is a picture produced by a D-Wave collaboration in Canada. In a nutshell, what this is standing for is some triangular lattice with an Ising Hamiltonian with effectively planar order parameter psi defined per triangular plaquette of some two-dimensional lattice with about 2,000 quantum spins. All the spins are made out of several superconducting transmons. In the end of the day, simulating dynamics of a couple thousand, 1,800 or so effective logical qubits interacting through Ising interaction. The details are not so essential. I just wanted to show kind of a real-life picture of a planar, so at the quantum level, a snapshot as a result of measurement of 2,000 qubits in conjunction with sort of natural thermally driven evolution as a function of temperature in this circuit. There's kind of a snapshot of XY order parameter distribution in the quantum annealer that shows kind of like domains. So here primarily order parameter is pointing kind of up or to the right and sort of twisting around a little bit, and you clearly see some points which they identify as vortices, anti-vortices, etc. And the main focus of this paper was on BKT, Berezinski-Koster-Staulis physics. That's the main claim of this paper. It's exactly the system that would also play out in terms of vortex motion and associated winding dynamics also for our proposal once we go beyond sort of natural thermal fluctuations and add some extra knobs. For example, torques at the boundary. We have some ideas how to do it that would drive such vortices out of equilibrium and allow us to construct to kind of build up sort of circuits, kind of dynamical non-equilibrium circuits out of the system. So that's an example of kind of like an artificial material where this physics can play out. I'm not going to go into the details also of some kind of real materials. Manganese 3tin, manganese 3 germanium is a very promising kind of Kagome frustrated like a family of frustrated antiferromagnets in which the order parameter is effectively captured in this kind of XY fashion, and because of very weak planar anisotropy, this kind of effectively XY dynamics of the frustrated order parameter, we think that these are very promising materials for the kind of large angle, highly out of equilibrium, kind of scalable vortex and winding transport dynamics that we are needing for our proposal. So that's an example of that. Okay. One can think of other types of topological textures, like I've already advertised. Our focus is on vortices, winding. That's just a blueprint. You could think of other topological textures like skyrmions. You could go to into the, or you could go to higher dimensions like a three-dimensional system in which instead of vortices, in this paper we propose to focus on Hedgehog motion. The mathematics and the physics works out very much analogously. The disadvantage, for example, of three-dimensional systems is that we cannot go to fourth dimension to start producing curved spaces. Okay, with 2D, we have this additional degree of freedom of making curved films, curved structures, and utilize geometry. So that aspect will be missing in higher dimensional structures. But otherwise, the basic topological hydrodynamics is underpinning certain aspects of magnetism in 3D as well. We've utilized, just to make another kind of singular connection to real experiments, we've utilized these ideas to analyze some imaging, soft X-ray tachography imaging data from John Meow's group at UCLA. So again, these are pictures of real experimental data. The circles here stand for about 50, 60 nanometer large silica balls compressed into FCC lattice, the interstitial space filled up by nickel, exchange length about 10 nanometers, highly frustrated, highly non-collinear magnetic configurations arising as a result of this very non-trivial geometry of the interstitial space in the FCC silica lattice. We suggested to our experimental colleagues to characterize this geometry in terms of distributions of Hedgehogs and anti-Hedgehogs, fully analogous to the story for vortices and anti-vortices. There's also a generalized Stokes theorem that relates the Hedgehog distribution with a skyrmionic flux bounding some patch within which you're looking at the Hedgehog distribution. So just like you have a vortex winding intertransmutation, here you have a Hedgehog skyrmion density transmutation, and that turned out to be already a very useful perspective that helped our imaging colleagues. For us, was a little bit disappointing that these defects are, in the context of this experiment, are basically stationary defects and immobile. System is very frustrated, lots of topological defects, but they're frozen. So we see them, we categorize the statistics of the distribution. We see some tendency for Hedgehogs and the Hedgehogs to attract, Hedgehogs repel. That's all good. So all of the basic physical mathematical aspects are there. But at this point, here we have a kind of frozen configuration. So no real transport yet over here. Okay. So let me kind of skip through some details. For those of you that are not familiar with magnetism, it's worthwhile pointing out that people have been, over a number of years in magnetism, have been interested in so-called curvilinear magnetism, or magnetism associated with various non-trivial two-dimensional structures. For example, take a magnetic film, roll it into some cylindrical shape, and ask yourself what sorts of magnetic configurations, magnetic topological defects you get on the boundaries. That's already an established field. There's a book that came out recently reviewing the state of the art of this field. This is curvilinear micromagnetism. What we're proposing to do is taking this to the next level and doing spintronics in such curvilinear systems. So here, finally, I'm getting to one of the key punchlines of this talk. We believe it's a very rich the curvilinear, so non-equilibrium dynamics controlled by spin transfer torques using tools of spintronics might be a very fruitful playground. And finally, just to come back to my original proposal, tie this story to the notion of well, back to why do I have this helical wire wrapping around the cylinders? Let me just explain this point, and then I'm done with my talk. So why helical wire? Well, because I'm going to utilize a torsion of a curve. Torsion of a curve of this helical wire. This torsion, it's non-zero for a helical wire. It could be positive or negative depending on the handedness of this helicity. It turns out the coupling, the effective coupling between electrical current and vortex current is in this structure, in this curvilinear curve structure, is proportional to the torsion of the curve. So this calligraphic R is proportional to this geometrical object, and that gives us sort of a geometrical handle on the physics. Finally, the thermodynamic efficiency of the energy interconversion between the two circuits is parameterized in this fashion. I'm dropping some phonological prefactors here. In essence, the torsion, this geometrical torsion, is parameterizing the efficiency of the energy interconversion in this fashion, which has very much similar structure, for those of you familiar with thermoelectricity, to the so-called figure of merit ZT, the dimensional figure of merit that's proportional to Seebeck coefficient squared, very much like the torsion square here, except that now this is all geometrically controlled. That's it, and thank you for your attention.